Welcome everyone, welcome to my video on curvature. And today I would like to talk about an alternative method to proving this formula. And so, before I begin, let me explain why I even decided to prove this in the first place. So, this proof on the regular parameterization of curvature already exists everywhere in calculus textbooks. However, I didn't really like how they proved it though. And the reason though is because they kind of knew in advance what the equation was and then they just showed that it was equal. And of course, and for more content about that, please look at the PDF that I put in the description below, and you can check that out. All right, anyway, so let me get started on proving it. So first, let me quickly show the theorem. So the theorem of the regular parameterization of curvature is that let the position vector r of t be a regular parameterization. And the word regular parameterization is really just a fancy word for saying that r of t just changes with respect to time, i.e. the speed, the r prime of t is not equal to the zero vector. Or, worded differently, the speed or the magnitude of r prime of t is simply not zero. That's it. Okay, and let's just assume this was true. And then for that case, we know that kappa, yeah, so this Greek character is known as kappa, and basically, this is denoted commonly denoted as curvature, but this is simply equal to the magnitude of the cross product of r prime of t and r double prime of t, and then we divide that by the speed, or basically r prime of t magnitude cubed. And so today I would like to prove to you that this formula itself is true. So that's my goal. Okay. All right, let's get started. So here we go. Let's start our proof. And let me make sure I get a little bit. There you go. All right. So before I start, since I'm going to get started right now, the first thing I need to talk about is that we need to talk about the definition of curvature, and that is kappa, or the curvature, is defined as the magnitude of the unit tangent vector with respect to distance. And you might be wondering, why are we defining it in terms of distance and not with time? And that's a good question. And the reason is simple. It's basically because we want to make sure that we measure the curviness at a specific point independent of velocity. For example, consider this point here. And then if you can, and we know that at this point there's got to be some kind of curvature existing, right? Because if there wasn't, then this particle couldn't have started bending at that time. And so imagine that for example, let's just suppose that the supposed curvature was dependent on time. Let's see what will happen. Well, if this was dependent on time, imagine that for our first instance, our velocity was like, say, 1. Then it might go like this much. But imagine in the second instance, our velocity was much quicker though. Then because the speed is bigger, then we might suppose that this thing will be changing, will be different than from the first instance. But we don't want that, because we want to make sure that we only measure how much the curve is bending, not how quickly the particle is traveling. And so that explains why we want to make sure that the curvature is independent of velocity. So hence we use s, because it's just arc length, and we can usually assume to be independent. So great. So this is the definition of curvature. Okay, but of course, like I told you, since kappa is a function of time, it would be better if you can write this as a function of time. So hence we start with the chain rule. So we might be like, okay, well, what happens if we take dt over dt? Well, as we know from calculus, if we use the single variable chain rule, it becomes dt over ds times ds over dt. ds over dt is basically speed. So this is the same thing as dt ds times speed, which is... And of course, we need to take the absolute value here, so we take, not the absolute value, sorry, the magnitude, so we put the magnitude on both sides. And of course, we know by definition, this is kappa. This is the curvature. So hence, curvature is essentially the time derivative of the unit tangent vector on its magnitude divided by the speed. Hopefully you can imagine what I'm going to say next. Basically, what we have to do next is figure out what is this. In other words, how can we rewrite the magnitude of the derivative of the unit tangent vector with respect to time in a different manner. So let's just start with taking the time derivative of the unit tangent vector with respect to time. And in this case, I am going to omit the magnitude sign just so it's easier for us to compute it, and we will come back and we will apply the norm operator later, so that way we can make sure it's consistent. So first, let's take the derivative. So we know that by definition, the unit tangent vector is r prime of t divided by the speed. And of course, assuming that the speed is non-zero, we can rewrite this as r prime of t times the speed to the power of -1. And of course, if we use the product rule, we can get r double prime of t times the speed to the power of -1 minus, right, because you need as the power rule, and that becomes r prime of t to the -2. But then by using the chain rule, we have to multiply by the derivative of speed. And then, of course, we need to include r prime of t. Great. So, and just keep in mind that we were taking the derivative of the unit tangent vector. So great. At least we have something to use. So now our next question is well, what is this? Is there a way to simplify it? And so now we will focus on this part. So first, let's take the derivative of the speed. And this isn't as straightforward as you think. One thing to note is that this is not the same thing as the magnitude of the acceleration. That is not true. Please make sure you don't make that mistake. It's not the same thing. Okay. All right, but in order to do this, let's first define something, and that is, let's define r of t to be equal to x of t, y of t, and z of t. Oh, and by the way, we're assuming that this is in 3 dimensions, but if it was an R2, you could have simply just done x of t, y of t, and it would have just been a 2D vector. And of course, the derivative, which is r prime of t, is simply just the derivative of each component. And I omit the t just for simplicity. And of course, from the definition of vectors, we know that the magnitude is simply x prime squared plus y prime squared plus z prime squared. And so now we will rewrite this as the derivative of x prime squared plus y prime squared plus z prime squared. And using our single variable differentiation rules, well, first off, there's a square root, so we need to take the derivative of the square root itself. So hence that would be, well, since a square root is basically to the power of 1/2, so you bring the 1/2 down. And the components will end up, and then this thing inside will end up being to the -1/2, so then that will be the square root on the bottom. But of course, we're not done, because there's some stuff inside the square root, so we need to use the chain rule and multiply each component. So the derivative of x prime squared is going to be 2 times x prime. But however, there is an x prime inside of that parenthesis, so we need to use the chain rule again and multiply by x double prime, where x double prime is basically the second derivative of x of t. And of course, you do the same thing for y and z, so hence 2y prime times y double prime plus 2 times z prime times z double prime. And we can see some simplifications here. First off, notice that there is still this square root there, and we know that by definition, or by the item I just defined above, this is simply the speed. And if you look very carefully of the numerator, you can notice that this thing is really the dot product between r prime of t and r double prime of t, right? Because x prime belongs to r prime of t, and x double prime belongs to r prime double prime of t, and you're multiplying them together. And we know that the definition of dot products is that you just multiply each component together and you add them up. So this makes total sense. And so hence, and you can also see the twos cancel each other out, so it ends up being r prime of t dot product of r double prime of t divided by the speed. Great. And so now we will plug this thing back up here, right? Because that's what we wanted to find in the first place. So then continuing, I will write dt over dt. And I'm rewriting this, so then it's the acceleration times the speed to the -1 plus, no, sorry, minus and I put a arrow here so I include some more stuff here. And yeah, and then we include this, and then we have to multiply by r prime of t. So let me first put r prime of t and times that. So then that times of course, this looks a little bit messy, so let's simplify it a little bit. So hence we can rewrite this as r double prime of t divided by the speed, and then minus r prime of t dot product of r double prime of t times r prime divided by r prime of t. So continuing, we get, oh, and also let's also factor out that speed on the bottom, so we get 1 over r prime of t magnitude, and hence we get r double prime of t minus r prime of t dot product of r double prime of t over speed squared times r prime of t. And now let me explain why I factored out the 1 over r prime of t, the speed, in the first place. Well, this vector here is very interesting. And the reason why I say so is because this is actually the vector that is orthogonal to the projection of r double prime of t onto r prime of t. Okay, if you thought that was a little bit wordy, let me explain it with a diagram. So first consider this diagram that I'm about to draw, and let me do it with a different color so it's easier for you to see. So just consider a curve, maybe like that. And I'll just call, and maybe there's the XYZ plane. And consider this point right there, right? And then we know that if the curve is traveling in this direction, then we know that r prime of t is traveling this manner. And let's just suppose that maybe r double prime of t was here. Then what happens is that this vector, and let me do it with a different color because I don't want to overlap it too much. This red vector is actually the projection of r double prime of t onto r prime of t. Basically, it's just basically the vector of r double prime of t that's kind of shadowed onto the direction of r prime of t. And basically this amount is actually equal to and interestingly, this projection is actually equal to that amount. And so then you might wonder, okay, then that means I need to subtract r double prime of t and the projection. And that only tells us one thing, that this vector here is actually the vector that is orthogonal to the projection of r double prime of t onto r prime of t. So actually, this blue vector is actually this whole thing because we're subtracting those two vectors. And so now that tells us that we need to figure out something about this blue vector. So now let's consider going back to, so remember that this is essentially dt over dt. But of course, I promised you in the beginning that I have to take the absolute that I have to take the magnitude of this at the end. And now I would like to apply that operation right now. So if we apply the magnitude operator, that means that we need to apply the magnitude operator to this term and that term, or the blue vector basically. And so we get the magnitude of 1 over r prime of t times the magnitude of r double prime of t minus r prime, dot product of r double prime over the speed squared times r prime. Now, one thing I want you to notice is that this thing, the magnitude of 1 over the magnitude of velocity, is already itself a magnitude, so this thing can actually go away. And that will be valid mathematically. Great. So then our next question is, well, what's the magnitude of this thing though? At first they may not look very clear. So let's go back to that same diagram, and I'm going to redraw that same diagram, but now I'm going to add a geometric idea. And that is, hopefully it's similar enough, and I suppose it is. Okay, and I'll draw that again. So then r prime, r double prime, and the projection, and the blue vector. And remember, we want to find the length of this blue vector. That's our whole point of doing this. Now, you might think, okay, well, since I only need the length of this blue vector, we just need to use some geometric properties. And that is, imagine this length of r double prime, right? And that length is denoted by, oops, my bad. Let me change that. Yeah, the length is this much. And that's the length of here. And now let's introduce an angle theta, right? The angle between r prime and r double prime. Well, it turns out that the red vector, because it's like it's kind of like that. It's kind of like you're just projecting on it. So what happens is that the projection, the length of the projection is simply r double prime of t cosine theta. And that only tells us one thing, because we know that sine squared theta plus cosine squared theta is equal to 1, which implies that if you multiply r double prime of t on both sides, then you get r double prime of t, the magnitude, squared sine squared theta, plus that squared cosine squared theta. And that's equal to the square of the length of r double prime. And we know that because this thing represents the square of the projection, then this amount can only imply one thing, and that is it is simply the length of the blue vector squared. And so that means that we can simply replace this item with this amount, which is kind of nice, right? Because that's simply the length of the blue vector. So let's rewrite this. So dt over dt is equal to 1 over the magnitude of r prime, and then we replace this by r double prime of t sine theta. And now we have one last step, and that is, well, how can we rewrite sine theta in terms of r and its derivatives? Well, there's a rule in vector geometry that for any two vectors a and b, then the magnitude of the cross product is equal to the length of a times the length of b sine of the angle between the two vectors. And so this tells us that if we want to find sine theta, then it is equal to the length of that cross product divided by the length of a times the length of b. And so hence, if you plug that back in here, then we get, oh, sorry, and I forgot that this is supposed to be a magnitude. Right, and then we replace this with the fact that if a is equal to r prime and b is equal to r double prime, right, because those are the only two vectors that we talked about, then we can rewrite the sine theta, right? So now I'm going to write the sine theta here, and that is, it will be r prime times r double prime, all divided by the length of r prime times the length of r double prime. And we see two things. Oh, and sorry, I forgot that length there. Yeah, because it's supposed to be a length there. So sorry about that. Then we can see some things here. First of all, we see that this and this go away. Oh, sorry, that go away. And second of all, this becomes squared. So hence we get And now we realize that this looks very similar to the formula that I showed you in the theorem above. And so now we only need to do one additional thing. And that is if we go all the way back up to here. Notice we have just found this one, and all that's left is that we just have to divide it by the speed. So then we go back, and then we get... Sorry, that's a terrible looking kappa there. That is definitely not how you write that in Greek. There you go. Right, and then we know that this is the magnitude of t with respect, or the derivative of t with respect to time, divided by the speed. And if we plug that in there, then we get the magnitude of r prime times r double prime, all divided by r prime of t cubed. And that ends my proof. Okay, so to quickly summarize what I've been just talking about, I just want you to know that first of all, what we did is that we used the definition of the curvature, which is here, and then we basically took the time derivative of the unit tangent vector, and then we rearranged it so we get this. And then we took the time derivative of the unit tangent vector, and we try to simplify it as best as we can. And then we ended up with a geometric intuition that the time derivative of the unit tangent vector has some relationship to that blue vector, which is orthogonal to the projection of r double prime of t onto r prime of t. And then we simplified it a little bit, and then we used the length of the cross product to replace it with sine theta. And hence we ended it there. All right, and that ends my video. And hopefully you found this alternative proof to curvature much more algebraically and geometrically more intuitive and more, I guess, makes better sense than those on the calculus textbooks. All right, anyway, if you found this great, if you found this amazing and helpful, please put a like, please subscribe, and thank you for all your support. Have a great day, everyone. I'll see you again pretty soon.